Another important law which we use to determine the magnetic field B at any point P due to current carrying wire is the Amperes law, and it states that the line integral of the magnetic field around any closed path or circuit is equal to mu naught times the current I enclosed by that closed loop. So this law, which is called the Ampere's circuital law, it is applied to a closed path or a closed path is usually referred to as a circuit, so that is why it is also termed as Ampere's circuital law. This circle on the integral sign indicates that it is applied to a closed loop, which is shown in this figure. This law has analogy with the Gauss's law, which was used to determine the electric field in symmetrical situations. And here, if you remember, here we used, on this side we had E dot dA, and that was equal to 1 over epsilon naught times the total charge enclosed by the closed surface. This was the electric flux through a closed surface, and this is the charge enclosed by that closed surface. Here we are having, instead of E dot dA, we are having the line integral of B, which is equal to mu naught times the current, because now we are dealing with the moving charges or the currents. So instead of static charges, we have replaced that thing by I, and 1 over epsilon naught is replaced by mu naught, and this side is replaced by the line integral of B around the closed path, which is shown in form of a circle over here. If you look at this figure, B at any point, this circular ring is denoting the magnetic field, and if we consider the closed path also in form of this ring, then if we divide the ring into small length elements, and each length element is equal in size and is having the length dl, then dl at any point is tangent to the circle, and B is also tangent to the circle at that particular point. So both B and dl are in the same direction. So here B dot dl will be equal to B dl cos of 0. So at any point on this circular loop, which is the Amperian loop, B and dl will be parallel. It must be kept in mind that just as we chose a closed surface for applying Gauss's law, it is essential to choose a closed path for applying Ampere's circuital law, and that closed path is also called Amperian loop. Now let us apply this Ampere's law to determine the magnetic field due to solenoid. And solenoid is a spring-like structure, just as shown in this figure. That is a long wire wound in form of a spring, in which the turns are tightly wound, it forms a solenoid. So if the wire is carrying a current, then the current in this solenoid will be in form of rings, and the magnetic field will be in form of straight lines, just as we determined this direction of B by applying the right hand rule. So this is a solenoid which is a long wire wound in form of spring, and we want to determine the magnetic field due to this current carrying solenoid with the help of Amperes law. So the first step in applying the Amperes law is to choose a Amperian loop, and that Amperian loop in this case is this rectangle, which is having 4 length segments: AB, BC, CD, and DA. The long side has length H, that is AB and DC both are having the length H. So let's apply, and further the smaller side is having the width W. So if we apply this Amperes law to determine the value of the magnetic field due to current in this solenoid, we will evaluate the line integral along these 4 length segments and sum up the contributions to the line integral to have B dot dl, integral of B dot dl around this closed circuit, which is our Amperian loop. So let us first consider B dot dl for this line segment, which is AB, and here we are traversing it in the counterclockwise direction. So AB and the magnetic field B both are parallel here. The angle between B and DL will be 0 for this particular segment, and B dot dl will be equal to B dl cos of 0, which is 1. So we will have B dl, and dl is equal to H. So we will get BH for this particular segment. Similarly, over here, B and this segment is at 90 degree. These two are at right angles. That is our B, the magnetic field B, which is directed this way by right hand rule, and this segment is vertical, so both are making an angle of 90 degree. B dot dl will be equal to 0 for this segment. This particular segment is lying outside the magnetic field because all the magnetic field is inside the solenoid, and this segment is outside the solenoid, so B is equal to 0 over here. That is why B dot dl will also be equal to 0 for this particular segment. Again, this dA is perpendicular, just as this was perpendicular to the magnetic field. So B dot dl for this segment will give us 0 because B dot dl cos of 90 will be equal to 0. So the summing up all the contributions, we will just get BH for the closed integral of B dot dl around the closed loop. So let's now go to the calculations of this this whole process.